Hello and welcome back everyone to the YOLO Basic Terminologies video. In this section we will be talking about mean average precision or mAP. Before we start talking about the mean average precision, we need to learn some acronyms like true positive, false positive, true negative, and false negative. So in classification, we use something known as a confusion matrix. So a confusion matrix is basically constructed by using these four values. So for example, if you have a prediction that says hot dog and not hot dog, so we have two classes, and true positive means when the prediction and the ground truth value are the same, and a false positive value, which is shown on the image, which is shown to the right of the hot dog. So if you have a popsicle input and then the prediction is a hot dog, that's a false positive because the image is showing a popsicle and then the model is saying it's predicting a hot dog. And false negative is that if the ground truth is saying that it's a hot dog and the prediction of the model is giving you a negative value, such as not hot dog, that's a false negative. And then a true negative is if the image is not a hot dog and the prediction is also not a hot dog, so that's called a true negative. So what about how do we use these values in object detection? So true positives, these are just the predicted bounding boxes which have an IOU greater than 0.5 with the target bounding box for a given class. So if you have two bounding boxes and the first one is the predicted bounding box and the other one is the target bounding box. The target is the ground truth bounding box, and if the overlap between the two is greater than, or the intersection over union is greater than 0.5, that's a true positive. And false positive in the sense of object detection is if the predicted bounding box has an IOU less than 0.5 with the target bounding box. And a false negative value is when there are no predicted bounding boxes for a target bounding box. So false negatives are just considering the ground truth values without considering the predictions. So note that we don't use the true negative values in object detection and segmentation because it is correctly detecting the background of an object as a background. So on the image above, we can see that the IOU is 0.96, which means the overlap between the prediction box and the ground truth bounding box has an overlap that is greater than 0.5. So it is a true positive. And on the second image, we have an IOU of 0.22, and the overlap between the two boxes is less than 0.5, so that's a false positive. And on the third image, we have just the ground truth bounding box and an IOU of 0 because we don't have any prediction boxes, and that's a false negative. So we don't use true negative because it means we didn't output a bounding box when that bounding box wasn't there. So it doesn't make sense to use true negative in object detection. So once we have sorted out the meaning of true positive and false positive and true negatives and false negatives, the next concept to consider is precision. So precision measures the proportion of the predicted positives that are actually correct. So if the predicted positives, which are the true positives that are outputted by the model, and we take the ratio between the true positives and the total positive results, That's called precision. And the total positive results is just the sum of the true positive and false positive values. So if you're just wondering how to calculate precision, it's just simply the ratio between the true positives and the number of total detections from our model. So the predictions might have, some of the predictions might have an IRU greater than 0.5. Some of them may not have an IRU greater than 0.5. So we just sum all of the predictions and use it as a denominator in order to compute the precision. And recall measures the proportion of the actual positives that were predicted correctly. So it's just the ratio between the true positives and the total number of ground truth boxes in our detection model. So recall is defined as the ratio between true positive and the sum of true positive and false negative. But in this case, in the denominator, we just replace the term by just counting the number of total ground truth boxes. Now that we have covered the concepts of precision and recall, we can talk about average precision. And average precision is a popular metric which is used in measuring the accuracy of object detectors like YOLO, FASTER, or CNN, and SST. And average precision is not the same as the average of all of the precision values, as we might assume from the name. It's just, it computes the area under the curve, under the precision and recall curve. So it's considering both the precision and recall values and not only the precision values. So average precision computes the average precision value and for recall values between 0 and 1 over the range 0 to 1. So let's take a look at one use case for average precision. So this is an image, and the YOLO V5 nano model is predicting the bounding boxes on the objects, and we use an IOU threshold of 0.5. The ground truths are already known. So if we put the ground truths and the predictions given by YOLO V5 nano side by side, so we can see that the ground truth boxes are given for a person, and we also have a person inside the car, and then we have another bounding box which is capturing the truck, and then we have a teddy bear, and then we have dogs. So these are the objects that are labeled as ground truths. And on the prediction, which is given by the model on the right side, we can see some of the predictions for the dogs are not correct. Some of them are given as a sheep, and some of the predictions might not be the same as the ground truth objects. So we can see that the images have the following objects. We have 2 people, and we have 12 dogs, 1 teddy bear, and 1 truck. And the YOLO V5 nano model has predicted the following objects. So we have the person, the dog, the teddy bear, the sheep, and the truck. So how do we compute the average precision? The average precision is always calculated class-wise. So when we compute the average precision, we have to compute each class independently, and we cannot combine all of the classes, measure the precision value, and compute the average precision. So for this particular use case, we're just going to compute the average precision for a dog class. And the steps to be followed are, on step 1, we record every dog detection along with the confidence score. So these are all of the dog detections that are given by our model. And at the bottom, we can see a list of confidence scores. So the confidence scores just tell us whether there is an object within the box. And the true positive and false positive labels are given to each of the detections for the dogs. So if the IOU of the predicted box matches the ground truth by greater than the IOU threshold, then we label that detection as a true positive. And if the IOU of the predicted box matches the ground truth is less than the IOU threshold, then we label that a false positive. So depending on whether the predicted box is overlapping the ground truth box, and by computing the IOU using the overlap and union, and comparing it with the IOU threshold, we can label each detection as true positive and false positive. And on step 2, we sort the table in descending order of the confidence score. So just as we did in the previous video when we computed the non-maximum suppression, we did the same thing in which we list all of the detections in descending order of confidence score. So the highest confidence score will be at the top and the lowest confidence score will be at the bottom. We tabulate cumulative true positive and false positive. So for example, on the first row, we have the label is given as true positive, and the cumulative true positive is just the number of true positives up until that point. So in this case, we just only considered one row, so we have one true positive. And after the second row, we have a false positive, and the cumulative true positive will stay the same as 1. But the cumulative false positive will increase by 1 because we have one false positive now. And on the third row, we add another true positive, and we add 1 to our cumulative true positive. And then we just accumulate the number of true positives and the number of false positives and write them out and tabulate them next to the matches. And on the third step, we calculate the row-wise precision and recall by using the formulas we have seen in the previous section. So in order to, we use the cumulative true positive as a numerator to compute the precision, divided by the sum of the cumulative true positive and cumulative false positive. So on the first row, we have 1 over 1 plus 0, which gives us a value of 1. And for the recall, instead of using the formula given in the previous section, we're just going to count the total number of ground truth bounding boxes. So in total, we have 16 ground truth bounding boxes. So it's just going to remain the same for the remaining computations that we're going to perform. So it's TP divided by the ground truth boxes. So on the first row, we compute the recall by using 1 true positive divided by 16, the total number of ground truth bounding boxes. Next, we plot the precision and recall graph for each of the detections. If the table contains multiple precision values for the same recall values, you can consider the highest value and discard the rest. So for example, in the previous table, we can see that for the same recall value of 0.08, we have different precision values. So for the first one, we have 1, and for the second one, we have 0.5. So in case you have the same precision value, no, the same recall value, but different precision values, you have to select the one with the highest precision value and remove the second one. So that's what we did on the next step, but not doing so will not affect the final result. This is just for simplifying the plot. So in our case, we're plotting everything. We consider both values. On the fourth step, we calculate the average precision by using a method known as 11-point interpolation. So the 11-point interpolation method was introduced in the 2007 Pascal VOC challenge, image detection challenge, and the precision values are recorded across 11 equally spaced recall values, and a prediction is positive if the IOU is greater than or equal to 0.5. So what's new about the 11-point interpolation? So the first thing that we need to do is divide the recall value, which ranges between 0 and 1, and divide them equally into 11 points using a range of 0.1. So you have 11 points starting from 0 up to 1, such as 0, 0.1, 0.2, and so on. That's the first step, and we put it on the x-axis. And next, we compute the average of the maximum precision value for these 11 recall values. So the average maximum precision value can be the interpolated precision. So what is the interpolated precision? It's just a fancy name to represent the maximum precision corresponding to the recall value greater than the current recall value. So we're going to see a graph which is going to show us how we compute the interpolated precision. So in simple terms, it is the maximum precision value to the right. So in this graph, we can see that we have 11 points on the x-axis, as we have mentioned before, values ranging from 0 up to 0.9. And we have a graph, and this graph shows the precision values for the recall for all recall points. So as you can see, this precision value forms a zigzag shape, but we're just only considering the precision values at these 11 points. So we can see that from 0 up to 0.4, the precision value remains at 1, because that's the maximum value up until that point. Then it goes down to 0 at 0.4, and then it increases linearly, and then it stops at around 0.8. So the interpolated precision is whenever the precision value falls, we just consider the highest, the maximum precision value to the right of the current recall value. So for all the points, until we find the next maximum precision value, we're just going to assign those recall values as that maximum precision value. So for all the points between 0.4 and 0.8, instead of considering the real precision value, we just consider the maximum precision value. So at points 0.5, 0.6, and 0.7, the precision value is going to be at 0.6, which is going to be the same. And at 0.8, the precision value falls again to 0. And in this case, we wait until the precision value increases again. And then when we get the next maximum precision value, we assign all the points next to the current recall value the same as that maximum precision value, which is 0.5. So there are two major concepts that we need to consider when we talk about 11-point interpolation. First, we just need these 11 points, 11 recall points. Second, we need the interpolated precision. And what this interpolated precision means is just the maximum precision value next to the current recall value. And there is an easier way to find the 11 interpolation points. So for example, you just extend a line from the maximum precision value to the next vertical line. So as we can see from the graph above, we can extend all the points, all the maximum points to the next vertical line, and then put dots on the horizontal lines at each interpolation, 11 interpolation points. So that makes it easier to find these interpolated precisions. So you might ask why precision is interpolated only for 11 recall points. So quoting from the paper, the intention in interpolating the precision or recall value in this way is to reduce the impact of wiggles in precision or recall curve caused by small variations in the ranking of examples. So as we have seen in the graphical depiction, we saw that the real precision values have some kind of zigzag lines, wiggle lines, and we don't want them when we are calculating the average precision value. So we just consider 11 recall points. In reality, the evaluation data set is huge, and when we plot the graph for all predictions, the difference between adjacent points will be very, very less. Hence, to compare two models, 11-point interpolation is sufficient. So when we consider broader examples and the data set is very huge, it's going to be very difficult to compute the average precision. So we just need 11 points to compute the average precision. Second question you might ask is average precision calculated for all points as well? So yeah, it can be computed for all points, not only by just using these 11 points. And this problem was figured out on the next paper by Pascal VOC in 2008. So the 11 interpolated method suffers from two issues. The first one was it was less precise. So second was it lost the capability in measuring the difference for methods with low average precision. So a different average precision calculation was adopted in the 2008 Pascal VOC. So the average precision can be computed by using a different method to the 11-point interpolation method. And that method is known as area under the curve, or AUC. So for later Pascal VOC competitions, VOC 2010 up to 2012, it samples the curve at all unique recall curves whenever the maximum precision value drops. So instead of just considering those 11 points, it considers all of the points, all of the recall values between 0 and 1. So with this change, we are measuring the exact area under the curve, under the precision recall curve, after the zigzags are removed. So we're going to use the same examples that we have used in the previous section. So previously we just computed 11 points, but now we're just going to use integration in order to compute the area under the rectangle where the precision value drops. So for example, between the recall values R1 and R2, we take the difference between these two recall values and use it as a width. And the height will be the maximum precision value next to the current recall value, which is R1. So when we reach R1, we try to find the next maximum precision value, and it's going to be in R2. And we extend we draw a line from this point to the next vertical line on the left and try to compute the area of that rectangle. So the area would just be the product of the width and the height. So no approximation or interpolation is needed. Instead of sampling 11 points, we sample a lot of interpolated precision values. And whenever it drops, and we compute the average precision as the sum of the rectangular blocks. So we compute the area of different rectangles in different sections of the graph, and then finally we sum the area of these rectangles. So in this case we have 3 rectangles and we sum them together. So this is the formula, and this, the difference between Rn plus 1 and Rn is just the difference between 2 recall points, and P interpolated is just the maximum precision value. And this definition is called the area under the curve. So using our previous example, let's try to compute the average precision using the precision and recall values. So plot the final interpolated graph and calculate the average precision for the dog class. So we have a list of all the precision values and recall values, and we plot them on the graph. And it's given on this diagram. So in order to compute the average precision for the dog class, we use 11-point interpolation. So we have for 4 recall values, we have a value of 0.71 as our precision. And so we multiply 0.71 by 4, and then we sum it with the next precision value, which is 1. And then for the rest of the points, we have a precision value of 0. For 6 points, we have a value of 0, so we multiply 0 by 6. Then we divide it by 11 in order to find the average precision. And in this case, for the dog class, we have an average precision of 34.9%. So similarly, by using the same procedure, we can compute the average precision for the rest of the classes. For person, the teddy bear, the sheep, and the truck. So make sure to calculate the average precision for at least 2 classes for a clear understanding. And once done, we will proceed with calculating the mean average precision, which is the title of this video. So after computing the precision, the recall, and the average precision, the final step will be to compute the mean average precision. And the mean average precision is just a simple concept, and it's just the average of all of the average precision for all of the detected classes. And it's given by the formula by the sum of the average precisions divided by the number of classes. So in the previous slide, we have computed the average precision for different classes. And since we have 5 classes, we sum all of the average precision values and divide it by 5. And in this case, the mean average precision is given as 47.88%. So to arrive at the mean average precision while evaluating a model, average precision is calculated for each class separately. Now, you might ask why average precision is not calculated for all the classes at once. So let's think about what happens if we do. You can go back to the detection chart and calculate the average precision by combining all of the classes. However, this time, well, we would not be able to observe the class-wise performance. So let's just consider a smaller data set having three classes, such as apple, bird, and butterfly. So let the number of training images for each class be 1,000, 20, and 1,000 respectively. So the model is bound to perform poorly for recognizing birds since their number is too small. So if you combine all of these classes and compute the average precision for all of the classes, the birds are not going to be considered in the evaluation of the average precision. So this can be identified only when per class average precision is calculated for each class. So another way, until now, the matrix introduced by Pascal VOC was the standard benchmarking system. However, with time, the models started saturating, and it was observed that even models with equivalent scores were not performing equally. So MS COCO datasets was introduced the 101-point interpolation average precision in 2014. So the COCO dataset was provided by Microsoft, and the 101-point interpolation average precision is just a better approximation of AUC under the PR curve method that we have seen previously. Moreover, COCO made the challenge tougher by redefining the mean average precision at 0.5. So before, when we computed the average precision, in order to label all of the classes as true positive and false positive, we only used a threshold value for the IOU as 0.5. And the mean average precision computed at that IOU is just given as mAP at 0.5. But on the COCO dataset, they used different IOU thresholds. So earlier, mAP was just evaluated only at an IOU threshold of 0.5. But for COCO dataset, they used 10 different IOU thresholds and then average all of the mAPs computed. So the mAPs were computed for IOU thresholds ranging from 0.5 to 0.95 at a step frequency of 0.05. Note that MS COCO defines average precision as mAP at, in square brackets, we put 0.5. 0.05 is the number of steps, and the final point will be 0.95. Here the terms average precision and mean average precision are used interchangeably, so we can call mAP as AP, it doesn't matter. Apart from this, MS COCO has 12 different metrics for evaluating object detection models. So instead of just considering the IOU threshold in order to compute average precision at different threshold values, they use different methods, different evaluating metrics, such as by considering the scales. For example, they computed the average precision for small objects, medium-sized objects, and large objects. They also computed the average recall and also using AR across different scales. So there are 12 different metrics used for the computation of mean average precision. So that's all about the YOLO Basic Terminologies section. In this section, we have covered all of the concepts starting from activation functions. Then we proceeded and reviewed some of the concepts about IOU and mean IOU non-maximum suppression and mean average precision. And starting from the next section, we will start to talk about the different versions of YOLO. Thank you for watching this.